Hello, Year 12. Good morning. I'm back. I haven't spoken to you for a while, but I'm going to record one of my videos today on partial fractions. It seems a bit random that we're moving from Maclaurin's to partial fractions, but if you check the scheme of work, you'll see that under the Unit 4 scheme of work, under the section for Maclaurin's actually has partial fractions in it. This is preparatory really for integration topics to come later. But I thought we'd get out of the way because we've only got a week to go to the end of term, and I wanted to do something with you that was quite self-contained and we could sort of knock off in a couple of lessons. So we're going to try this today and see what you think of it. I like this topic. The Mrs. Rand stuff, I think I've decided which direction I want to go in now. So I will be publishing some extra stuff to do on this lesson to do with that as well. For you to look at, and then we'll come back and talk more about that on Wednesday. I've decided, I think, to go with the Further Maths textbook, the AQA text, which is how I used to teach it when I did Further Maths before we moved to WJEC. You'll see what I mean, though, when we get to that. So anyway, partial fractions. So you will have met partial fractions already at A level. In fact, I think you might have already done the Year 13 partial fraction stuff, which is the following: a denominator containing linear factors, things like x plus 3, x plus 4. There could be a repeated factor, that's Year 13 only, and I think you've done it now, where you get something like x plus 3 squared. But crucially, the numerator is always a lower degree polynomial than the denominator. That makes it a proper partial fraction as opposed to an improper partial fraction, which we're going to have a look at today. Very excited. Now, a further maths then. The denominator contains linear factors still, but you could also have a quadratic factor of the form ax squared plus b. Not ax squared plus bx plus c, but ax squared plus b. That's an x squared term and a constant. That's what we've got to be able to deal with, and it's a very useful thing to be able to deal with for some of the integration that we've got to do. But also, and this is the other thing that's different, is that the numerator could be the same degree as the denominator. In fact, it could even be a higher degree. And I'm going to do an example where it is a higher degree today to show you how you deal with that. It's quite interesting how you actually cope with that and turn it into a partial fraction thing. So anyway, two examples. This one's from the integral maths, which I'm going to put the notes for in this assessment, as well as the exercise that goes along with it. So this is the one I'm going to do from there. So just take you through this, and then I'm going to do another one that's this is a proper one, so that the numerator is a lower degree than the denominator. It's a linear on the top and a cubic on the bottom. But I'm going to show you one where it's not like that, which is going to take a bit of time because it's quite a hard one. But I'll show you that after we've done this one. So very, very simple. You start off by splitting it into two separate fractions on the right hand side with an unknown numerator. The denominators are the same as the denominators on the left hand side. So we get something like that. Now, this one is just going to be a linear fact. It's just going to be a constant, c. And this one's going to be different. This is new. This is going to be a linear factor on the top. So it's not just a, it's ax plus b. Hence I use c there to leave room for me a and my b. Okay, so that's what you get. So that can be written in that form where a, b and c are constants, and we just need to find what those constants are to finish the question off. Okay, so what you do now is you turn this back into a single fraction by cross multiplying, getting a common denominator which will be the same as that. And when you do that, the top of the two sides would be 2x minus 7 on the left, and on the right it would be ax plus b multiplied by x minus 1, and it would be c multiplied by x squared plus 4, like that. I haven't written the denominators, they would be the same, so they kind of cancel out. And then, very much like you did for the partial fractions you've done so far, all you need to do is to substitute cunning values of x that will allow you to discover the values of a, b and c. And the first cunning value I'm going to use is the one that will eliminate both a and b in one foul swoop, and that is to substitute x equals to 1, because that will make that bracket 0 and all of this stuff will disappear. So if I let x equal 1, then on the left I will get 2 times 1 minus 7, which is minus 5, and on the right I will get 5c, like so. Therefore c is equal to minus 1. Okay, so I started thinking of something else then. Back on track. So c is equal to minus 1. Now we need to discover the values of a and b, and to do that we're going to need to sub in another cunning value of x, and the cunning value of x this time is x equals 0. Hopefully you can see why. It's going to make the ax term disappear, and I'll just have the b. So if I put x equal to 0, I will get minus 7 on the left is equal to, and on the right I'm going to get minus b. You stick a 0 in there and there, you get minus b, and then it's going to be plus c, which is actually minus 1. So minus 1 multiplied by 4, so bracket will be 4 like that. So therefore minus 7 is equal to minus b minus 4. Therefore add 4 minus 3 is equal to minus b. Therefore b is equal to 3. I think I did that right. Did a bit quick, but just check. Minus 7 equals minus b minus 1 times 4 minus 4. Add the 4 is minus. Yeah, I think that's right. Okay, and then finally, to find the a, it doesn't really matter what value of x I substitute in. Something simple. That's not going to give me too much headache. Or let's go for x equal to 2. Okay, so if I put 2 in on the left hand side, I'll get minus 3. And if I put 2 in on the right side, I'll get 2a plus 3 in a bracket multiplied by 1. Yay! That's good. 2 minus 1 is 1. That's easy to deal with. And then here I'll get minus c, which is minus 1 times 8. Like that. Therefore, minus 3 is equal to 2a, and it's going to be plus 3 minus 8, which is minus 5. Add the 5 on, gives me 2, equals 2a. Therefore, a is equal to 1. I have found my values of a, b, and c. Now, if Sir was not being incredibly lazy, he would now write out the answer, which would be x plus 3 over x squared plus 4 minus 1 over x minus 1. Okay, and we've turned that into a partial fraction, which then we will be able to integrate really. So we'd be able to integrate this really easily by integrating these separately. This one is do you remember Miss talking about look and see, and she talked about the case where the answer is ln of something. This is one of those because the top is am I lying here? Am I saying that wrong? It might not be actually. So differential of the bottom. Oh yeah, you'd have to split it into two separate ones. It's not what I said. You'd have to split that now into two separate fractions, ax over x squared plus 4 plus b over x squared plus 4, and integrate them separately. But anyway, I'm digressing here from the main message, which is that you can write that as a partial fraction and you will be able to integrate this. Okay, so moving on now. Oh my god, I'm not sure I want to take this on. I'm going to take this babe on here. Now, I have found on the internet a PDF document that explains how you deal with partial fractions when you start with something like that, where the top is of at least the same degree as the bottom. In fact, in this case, it's one higher than the bottom. Okay, and there are various ways of dealing with this. One way of dealing with it is to start by doing polynomial division of this. Now, I think you did that last year in normal maths, in year 12, well, this year in normal maths, it's a method that you use for factorising cubics. You can do it that way, but it's a bit of a faff and it's quite hard work. So I'm going to do it the way that this PDF does it, which is actually quite a nice way of doing it. It works like this. What you do is you look at the question and you first of all decide what the degree of the numerator is and the degree of the denominator. And in this case, the degree of the numerator is 3 and the degree of the denominator is 2. The difference between these tells you of the extra bits to your answer beyond what you would have got if the numerator had been of a lower degree than the denominator. That probably makes no sense to you at all. So let me try and explain. If I just looked at the denominator, well, first of all, let me factorize the bottom, because that's the first thing you need to do, because we haven't actually got two linear factors on the bottom, but we have really, because it does factorize to x plus 2, x plus 5. Okay, so now it'll be easy for me to explain what I'm on about. Now, ordinarily, you would get two terms if the top was of a lower degree than the bottom. So if the top was just a linear or a constant, then you would get a over x plus 2 plus b over x plus 5. What you get when the top is of a higher degree than the bottom, or the same degree, is you get extra terms, extra terms that are of a degree that is the difference between the degree of the top and the bottom. So if they have the same degree, you get an extra constant. If the top is 1 higher than the bottom, you get a linear term. If it's 2 higher, you get a quadratic term, etc. Now this one is 1 higher, so I get an extra linear term in my answer. It doesn't have a denominator, so it's just ax plus b like that, and then you get your usual linear terms for the two linear factors on the denominator. So that will be the form of the answer to something that started like that. It might help you if you read the PDF that I've attached to the video, and it'll explain that probably better than I've just explained it to you now. But I found this example from somewhere, not from that sheet, and I'm going to try and do it now. We've actually done the hard bit, just getting it to look like that. From then on, it's the same method as we used in the last one. You start by cross-multiplying this to get it over the common denominator of x plus 2, x plus 5. So each of these terms on the top needs to be multiplied by x plus 2 times x plus 5. Okay, so each of them needs to be multiplied so that they have a common denominator of x plus 2, x plus 5, which means multiplying that by x plus 2, x plus 5, multiplying that by x plus 2, x plus 5, multiplying that just by x plus 5, and multiplying that just by x plus 2. In other words, the top, I'm not going to write out the denominators, become talk amongst yourselves. Well, I can't, I'm only just going to fit this in. There we go. Okay, like that. Okay, so I have multiplied through to make all of the terms here have a common denominator of x plus 2 over x plus 5. All that's over x plus 2, x plus 5. Same as that. I can cross them out. There you go. And now, to find a, b, c, and d, you do exactly the same as what we did in the last example. You choose cunning values of x that will allow things to cancel out and make it easier to find a particular value. So I'm going to start by using a cunning value of minus 5, because that will eliminate that term, and that term, and just leave me the d term. So minus 5 is my cunning value of x that I'm going to choose. So I'm going to sub it in here and here. I can ignore all of that because it's going to be 0 and just sub it in here. So I need to put minus 5 in here. So calculator out. minus 5 cubed. Can you see that? Oh, I had this problem earlier. You can't actually see what I'm doing. Minus 5 cubed plus 5 times minus 5 squared minus 2 times minus 5 minus 19 minus 9. So we've got minus 9 on the left is equal, if I put minus 5 in there, that's going to be minus 3. So it's going to be d times minus 3. And from that I can see that d is equal to 3. I can find c in a similar way by setting x equal to minus 2 to make the other 3 terms disappear. So once again I need to find the left hand side by replacing all the x's with minus 2. So I'll just come back through here and rejig this. Here we go. I think that's right. On the end, I think I've done more. Minus 3. So minus 3 is equal to, this term here is the 1, so it's going to be c. If I put minus 2 in there, that's going to be 3, so it's going to be c3. Therefore, c is equal to minus 1. Lovely job. Okay, so next I'm going to choose another cunning value of x, this time to make the a term here disappear by setting x equal to 0. Okay, if I set x equal to 0, this will disappear and I'll be able to find out what b is. So if I set x equal to 0, I'll get minus 19 is equal to, okay, so this is going to become 10b, and then this is going to become minus, so what did we say? It's going to be minus, it's going to be minus 5, get there in the end, c is minus 1, and this one's going to be 5, oh god, get me head around it, it's going to be 10, because d is, it's not going to be 10, is it? Sorry, it's going to be 6, okay, because it's 3 times 2. Right, there we go, we got there in the end. So minus 19 equals 10b, minus 5 plus 6, well minus 5 plus 6 is 1. So take 1 off minus 19 gets me minus 20. So minus 20 is equal to 10b, therefore b is equal to minus 2. We're nearly there, just got to find the a now. And to find the a, I can just choose any nice simple value of x I like. And just sub it in. I'm going to choose x equal to 1. So on this side I get 1 plus 5, which is 6. Take away 2, which is 4. Take away 19, which is 4 take away 19 is minus 15. So I get minus 15 is equal to, put the 1 in here, I'm going to get 10a. Put a 1 in here, I'm going to get 3 times 6, which is 18, times b, which is minus 2, so minus 36. Oh, God, it's complicated. If I put minus 1 in, I'm going to get 6 times minus 1, which is minus 6. And here I'm going to get 3 times 3, which is 9. There we go. So we've got minus 15 equals 10a minus 42 plus 9. Why can't I do minus 42 plus 9 in my head? I'm just losing the plot. I'm on my calculator here. It's minus 33. Oh my goodness. So minus 15 add 33 is 18. So 18 is equal to 10a. I'm not liking this. So a is equal to 1.8. 10 over 18. 18 over 10. Oh, that doesn't sound right to me. I will just go back and check that one, because I expected a whole number there, obviously, because it can't, it has to be a whole number. So let's just go back and check. I must have made a mistake. So what did we have? We had 1 plus 5, which is 6. Take away 2, which is 4. Take away 19, which is minus 15. So I've got the left-hand side right. Let's check the right-hand side. So oh, it's here, isn't it? It's not 10a. It's So 1 plus 2, which is 3 times 6, 18a. Oh, for God's sake. Still 1, 3, so 18a, yeah. So it's 18a. Oh, I bet you I've made mistakes elsewhere as well. Let's try the b. So this is 3 times 6, which is 18, times b, which is minus 2. So that is minus 36. So I've got that one right. Let's check the c one. So c was minus 1. So 1 plus 4 is 6. So actually that's definitely minus 6. And then d was 3. So that's definitely plus 9. Let's just check now. Minus 36 minus 6 plus 9 is minus 33. Minus 15, add 33, gives me 18. So we've got 18a, oh, that's better, 18a equals 18. Well, a equals 1. Hallelujah, praise the Lord. Right, again, Sir's being lazy. You should now write this out in full using the a, b, and c and d values that he's just found. And that would be the correct answer. That and that would be equivalent. You'd be able to integrate that. Boom. Job done. There are 3 of these super difficult ones I think that you can look at on that partial fraction sheet. They give you the answers, but you can check to see if you can do them. They're not as important today as the other sheet. If you've not got the time to do all of it, do the other one, the integral maths stuff. And look out for the stuff I've put on here for you to do for Mrs. Part of the course as well. Thank you for listening. Have a good day, both of you. Bye for now.